Saxon Algebra 2, lesson 116. Look, the sun is making some nice shadows on my paper, so I hope they don't distract you. I hope you find them relaxing. We're going to talk in this lesson about permutations and probability. This is a big change from the heavy calculation lessons that we've done lately. You know, we've been working on the logarithms and the exponential functions. This will come as a breath of fresh air. Probability, we've talked about. These are games of chance. They involve rolling dice and spinning spinners and flipping coins. They're very easy to imagine. It's very simple math. Just a little bit of thinking has to go into how we set up the experiments. Permutations, you're probably going to find to be very similar brain work as probability. Permutations are arrangements of things, and we're going to start by talking about those first. I don't believe we've covered them in the past, so this is new. Oh, look, I smeared my ink. That is just sad, isn't it? Okay, let's take 3 letters. Imagine them as Scrabble tiles, if you will. Little wooden chunks. Each one has a letter separated on them. The question we ask ourselves is, how many different ways could we arrange these? Now, we can do it the long way, and let's do that this time. We're sure not going to do this every time. Let's just imagine them. First, we could have the A in the first place, right? And then we could have A, B, C, like I've shown it. Or we could switch these two around. Right? Oh, I'm sorry, I wrote the same thing twice. A, C, B. Better. Okay, now let's move B into the first place and put them alphabetically, B, A, C. Or we could leave B in the first place and switch up. B, C, A. Right? Now let's move the C to the first place, and then we'll go alphabetical, C, A, B. And then let's revert, we'll leave C here and we'll switch these around so it's C, B, A. Now, we can puzzle and stew over this for quite a while, but we'll find those are the only 6 ways you can arrange these tiles. The 3 of them. Now, that's great. We figured it out. That's the right answer. But I don't want to do this every time. I don't want to try and list them out and think of them all. And heaven forbid we have more than 3 tiles. What if we had 10? No. There's got to be a better way, right? So here's the better way. The better way is that we imagine the arrangements like so. These are basically spaces that the 3 tiles can put into. We can fit these into these boxes. These look a little small, but you get the idea, right? We can put these tiles in these boxes. When we go to fill in the first box, how many choices do we have? Well, we could put in the A or the B or the C. That's 3 choices. Okay, so we've taken one of the tiles and we've put it in here. Now, how many tiles are there left to choose from in filling up this box? Well, now there's only 2, right? Because whether it's A, B, or C, we've put one of them in here. And now we only have 2 left for that box. And then when we get to this box, we've already placed 2 of the tiles in the first one, so we only have 1 left. Make sense? 3 choices, 2 choices, 1 choice. And to solve this permutation, we multiply those together, and look what we get. 6 ways, just like before. So it's nice when we can visualize all of the outcomes, but we don't want to do that every single time. That's too crazy, right? Now, we're going to come back to this example later. No, we're going to do it now. This is called calculating the permutation without replacement, meaning we only have 3 of these tiles. We only have 1 of each letter. We can't get multiple A's or multiple B's or multiple C's. We just have 1 of each. So this is called I write it like this: without replacement. Squeezed it in. But what if, instead of just having one tile of each, what if we had a big stack of them? We would call that with replacement. Because every time we take a tile and put it in our tray here, there's another one left behind. So this time, we have a lot more options. And before I calculate the options, I want to show you that John has been kind enough to write them all out. If we can repeat the letters, if we have a stack of those tiles instead of just one of each, look how many more combinations we can make. Like I said, he's been nice enough to list them all out. We're not going to, but he has shown us all the different ways that we could arrange those tiles if we're able to replace a letter once we've used it, right? There's like a little stack of them that keeps coming up. I imagine it kind of like, you know, those napkin dispensers, especially the old school ones that are kind of chrome. You'll see them in certain restaurants now, where you pull out one napkin and there's another one right behind it and another one right behind it and another one right behind it. A Kleenex box is another example. But I always imagine those chrome paper napkin dispensers. That's what replacement is like. We use one, but there's another one right there with each of the letters. So now, when we go to fill in our tray, when we go to the first spot, we have 3 different letters to choose from, A or B or C. We choose one, we put it in. Now, when we go to the second spot, nothing's been used up. Last time we'd used one of our tiles, but this time they keep popping up. So we still have 3 different tiles to choose from. And when we go to the last spot, we still have 3 different tiles. We have more than 3 tiles in the problem, but 3 different tiles, right? We have 3 choices, A, B, or C, A, B, or C, A, B, or C. Here, because we have just the limited 3 physical tiles, once we put one in, we don't have an unlimited. We're not using the pop-up dispenser here. So when we are able to replace the items that we're arranging in these problems, we have a lot more ways to rearrange them. Okay, so if we're able to replace the letters as we use them, we'll come up with 27 ways. If we just have the 3 physical tiles and no replacements, then we can only do them 6 ways. This information forms the basis of our problems, which we are now about to embark upon. Grace is having a serious nap over there. She just did a big moany growny. 116.1. How many different ways can the numbers 3, 5, 7, and 8 be arranged in order if no repetition? So that's the same as without repetition, no repetition. So there's no repetition involved in this. We just have one tile of each number. Okay. So that means we have a tray with the 4 spaces, and we're imagining how we could arrange these tiles. Okay, when we go to fill in the first blank, we have all 4 to choose from. Now 1 is used up. We only have 3 to choose from. Now 2 are used up. We only have 2. And then in the end, we just have 1. We multiply this together. And you don't have to write this again. Remember how I have been doing this? 4 times 3 times 2 times 1. You don't have to, just multiply all of those together. And we'll find that there are 24 ways. I do like to see the word ways written by your answer. John does that too, because it reminds us of what it is that we're calculating. Oh yeah, we're calculating the different ways these numbers can be arranged. How many 4-letter signs can be made from the letters in the word equal? If repetition is permitted. So I'm going to write rep okay. Now, this one's a little bit different because we have 5 letters to choose from, but we're making a 4-letter sign, which seems kind of weird. It's John's way of saying arrange them into a tray of 4 compartments. That's how I think of it. Now, when we go to put a letter in the first spot, we have 5 choices. We have our napkin dispenser here. So as soon as we use one of those letters, any one of the 5 we use, another one pops right up in its place. So now we still have 5 to choose from. Another one pops up. And as long as our napkin dispensers are properly filled, which they are, every time we go to fill in a letter in the tray, we have all 5 to choose from. So this will be, let's see, it's 5 times 5 is 25, times 25, that is 625 ways. Again, we're multiplying each of the elements together, but you don't have to show it separately. You can just multiply from there. This is correct. What I think is the charm of these problems, but I also get that it can be annoying, is that every one is a little bit different. You have to use logic and common sense with each and every one of these problems to kind of suss out exactly what's happening and how to draw the boxes. Is there repetition? Is there no repetition? How do the different elements fit in the boxes? You definitely need your thinking cap. Do people talk about thinking caps anymore? That fascinated me when I was a little kid. The teacher would talk about your thinking cap and I was like, I have no idea what that is. It just means think. A multiple choice quiz has 8 questions and there are 4 possible answers to each question. That's how multiple choice works, right? The first question, A, B, C, D. The second question, A, B, C, D. The third question, A, B, C, D. So that makes sense. How many permutations of the answers are possible? Okay, so what we're drawing now is a picture that represents the 8 different questions on the test. So I'm drawing 8 compartments in my tray, which represent the 8 questions. Now, this doesn't tell us if there's repetition permitted or not permitted, so we have to use, again, our logical brains. We go to the first question on the test. How many choices are there? A, B, C, or D? So there's 4, right? They tell us there's 4 answers for each one. So we can choose any of those. Now, when we go to the second question, how many answers are there to choose from? Well, there's still 4 answers, right? There's 4 new answers. So every question on the test is going to have 4 different answers. So we can see that repetition is allowed, so to speak, because every question has its own 4 set of answers. Again, we're having to use a lot of logic. Now, this number is big enough that I would not expect you to calculate it by hand. Well, I guess I would. 65,536. You could multiply, let's see, we know that this much is 16 and 4 more is 64. See what I mean? You could do chunks of this, like this is 64 and this is 64 and this is 16. So you could multiply those together. So it is possible to do these without turning it into each one an individual problem. Use your brain to simplify the answer. This is what you should get though. 65,536 ways. Okay, we have 2 more, and we're going to switch over and talk about probabilities. How many 3-letter signs can be made from the letters in the word numeral if no repetition is permitted? And we're making 3-letter signs. So that means our tray, so to speak, has 3 compartments, right? For each of the letters in the signs. Now, I just have to say this, if this is driving you crazy, obviously, some of these combinations that we're creating are going to be nonsensical, right? Like what if I choose N, M, and L? That's not a word, but we're not letting that silly constraint limit our mathematics. We're just looking at how many different combinations are there. So if these problems drive you nutty because some of them are a little illogical, I hear you, don't worry about it. Okay, so the signs we're making only have 3 letters. We have lots more than 3 to choose from, so that will factor into our problem, but we're only taking 3 at a time. No repetition, so that means that once we choose a letter, we can't choose it again. So when we go to put a number in our first box, or a letter rather, 1, 2, 3, 4, 5, 6, 7, we have 7 to choose from. Now we've used one of them up. So when we go to fill the second box, we only have 6 to choose from. And now we've used 2 of them up. So now we're down to 5, aren't we? That we can choose from to make our 3-letter sign. When we multiply this together, let's see, what I do is I do this, because that's 30, and then I can easily multiply 30 times 7 to get 210 ways. So there are 210 ways to combine these 7 letters into 3-letter chunks without reusing them. There's 210 ways. Aren't you glad we don't have to write them all out? I would cry. Okay, example 116.5. Jamie had 5 places to put items in her display. She had 38 different items. How many different arrangements were possible? Okay, I had a student once. Her name was Natalie Smith. She just graduated from college in Texas. Her family was getting ready to move to Texas when I was teaching her this, and it was perfect because she had her mom had a great big china cupboard with all kinds of things in it that she had been sorting through and, paring down as they were getting ready to move. And then there was a windowsill right next to the china cupboard that had places to display that you could have easily turned into a display space. So I drew a picture like this for Natalie. Imagine that this is your windowsill. And imagine that there was like a 3-dimensional display space that went across the windowsill, right? These are boxes. Right? Instead of it just being a flat windowsill, there was this cool like shadow box thing in there. And now we have places to put each of these 38 items that are still in the china cabinet. 38 items, and we're taking them 5 at a time, not tame. So how many can we choose? Well, in the first box, we could put any one of the items. So 38 different items could fit in the first box. Now, John doesn't tell us if repetition is possible or not, but we have to think logically again. If there are 38 physical objects, then they're not going to keep popping up like paper napkins in a Chrome dispenser, are they? That is not the way the real world works. So we can infer that there's no repetition. So when we go to fill in the next space, there's only 37 items, 36, 35, and 34. That's how many different items we have to choose from. This one I would definitely allow you to use your calculator on because the answer is there are 60,233,040 ways to arrange those items in the china cabinet into these 5 cubbies on the windowsill. 60,233, yeah, I'm just double checking. That's correct. That's a lot of ways, isn't it? And this is what I mean when I talk about the tray. I imagine it's a box. I imagine it's lying on its back and we're dropping the different numbers into it. So when we look down, this is what we see. This one, we're kind of looking into it more sideways. Okay, This is probability. We're going to expand on this a little bit next year and a little bit more in the year after. No, a little bit more next year. This is Algebra 2. But this is the most important part of it that we're learning now. We'll add some flourishes later, but this is the main concept of permutations explained to you as boxes on a windowsill. Let's talk about probability. We've talked about this before. As I said to you in my little intro, probability involves games of chance. Rolling die, flipping coins, that sort of thing. And so we can imagine what's happening pretty well. The whole concept is that all the outcomes are equally likely. There aren't a lot of things in the world beyond games of chance for which this is true. So for example, when I flip a coin, it is absolutely equally likely that I will get heads versus tails, as long as it's not some trick coin that I bought in a magic shop that is weighted to always land on heads or something. So real life is not like that, right? Real life is a little more unpredictable, but games of chance give us this perfect world where outcomes are equally likely. The way that we calculate a probability, we can write the probability of certain events are equal to the number of desired outcomes. And I'll review this in a problem. I know it's kind of confusing just to hear these words. It's a fraction, the number of desired outcomes over the number of total possible outcomes. Let's try a problem and it'll make a lot more sense. And we're at example 116.6. Okay, 2 dice are rolled. What is the probability of getting a sum of 7 so we're trying to find that. That's part A. And part B is we're trying to get a sum greater than 8. Okay, we're rolling 2 dice. This is important, and I'll show you why. If we're just rolling 1 dice, one die is what it's called. It's pretty easy to imagine the outcomes. We know that there are 6 sides to the cube, and it could land on any one of those 6 sides, right? And we know that the sides look like this. There's a 1, there's a 2, there's a 3, there's a 4. Are you having fun drawing these? I am. There's a 5, except I want to go back and color those in a little better. There's a 5 and then a 6. Boxcars, right? Beautiful. So if we want to calculate, for example, the probability of rolling a 4, that would be 1 out of 6 total possible, right? If we wanted to roll an even number, let's see, there's 2 and there's 4 and there's 6, that's 3 desired outcomes over total possible of 6, right? So it would be 3 out of 6, and then we could reduce it to 1/2. But we're trying to roll 2 dice, so we have to draw a different kind of picture. This would be the number that's showing on our first dice, and I've lined it up right under here so you can see. But we're rolling a second die too. 1, 2, I'm gonna have to squish them a little. we're rolling 2 dice. So that means that our calculation is a little bit trickier. If you roll 2 dice, you know that at the very worst, you're gonna get a 1 and a 1, and you're gonna be able to move 2 hops, right? I'm gonna make this a little thicker so we can see. These are the sums, right? If you roll a 2 and a 1 in Monopoly, you get to move 3 squares. A 3 and a 1 takes you 4. You add them together, right? So we can create this table that will show all the possibilities, all the different options that you might get when you roll 2 die in a game. What are we talking about? Life, Clue, Monopoly, what else? I can't even think right now. Lots and lots of games have 2 dice. Not Yahtzee. Yahtzee has 5 dice. That would be a different kind of picture. But any game that has 2 dice, this is what you do. If you roll a 2 and a 1, you get a 3. A 2 and a 2 is a 4. So we're just adding these together, right? And we find really quickly, oh, they make a very pleasant pattern because it's just going up by 1 every time. Now, some students think, I don't need to write this all out. I can imagine it. Well, that's a great way to get errors in your work. So please humble yourself to just draw this chart. Okay, when it looks like this, you're done. Sadly, I wish those didn't stick out like that. That makes me sad. Okay, so now we're trying to find these specific probabilities that John has asked us about. He wants to know what's the probability, when you pick up 2 dice and roll them, what's the probability of getting a move, a sum of 7? Well, let's go through and let's circle all of our 7s. This is A. I'm going to write, there's the problem. I'm going to write the answer down here. The probability of rolling a 7 is 1, 2, 3, 4, 5, 6 possible, those 6 desired outcomes. Out of how many outcomes in all? Well, 6 times 6. So that means there's 36. And if you wanted to count the squares, you could verify that. So the probability of rolling a 7 is 6 out of 36, which equals 1 out of 6. We reduce whenever we can with probabilities. So the probability of rolling a sum of 7 equals 1 over 6. Beautiful. What about what's the probability of getting a sum or a move, right? Because when we make a move, we always add them together. Greater than 8. Okay, so I wouldn't include 8, but I would include everything bigger than 8. So I'm going to start at 9s. We would include those. And we would include the 10s and the 11s and the one little 12. So now let's count out how many desired outcomes would satisfy this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of 36, again, 36 possible moves. And this will reduce to 5 over 18. Okay, so the answer to this probability is 5 out of 18. This one is 1 out of 6. Okay, so we use this formula, and we have to be able to imagine all the different outcomes. We have to be able to visualize them. Is most helpful, especially in a crazy situation like this. I think we did this one last year. It's a good one. Okay, the last two problems, deal with a situation where you're playing one of these games of chance and you want to know what would happen if you did it multiple times. Let's look at example 116.7. We have a fair coin. That means you didn't buy it in a magic shop and it's not going to flip automatically to heads more often than not. A fair coin means just no cheating. It's tossed 3 times. What is the probability that it comes up heads every time? So We're trying to find the probability of heads, and then heads, and then heads, right? 3 times. So here we're going to imagine our 3 coin tosses. Now, in the first coin toss, what's the probability that the coin will come up heads? Well, that's 1 desired outcome out of 2 possible outcomes, right? It's either going to be heads or tails. No matter how many times you flip the coin, the probability of that particular coin toss being heads is always 1 out of 2. Even if you got tails 18 times in a row, it's still 1 out of 2. Even if you got heads 56 times in a row, it's still 1 out of 2. You're just on a weird streak. But that doesn't change the probability. Each individual flip of the coin has a probability of 1 out of 2. So that was true the first time we tossed the coin. It was true the second time we tossed the coin. And it was true the third time. This is the probability of getting heads. This is the probability of getting heads. This is the probability of getting heads. The probability of getting heads 3 times in a row, we multiply them. And look, I already put the dots in. So if we multiply them, the probability of getting heads and heads and heads is 1 over 8. And I meant for the equal sign to go there. Right? I multiplied those 3 together. So that's our answer. All right? Remember that previous events have no effect on each individual coin toss. The fact, for example, with this one, the fact that we got heads in a row twice before, it doesn't matter. It doesn't change anything. Okay, let's do one more of these. We call that idea independent events. The fact, it doesn't matter what you flipped in the past. That is the nature of probability and game theory, is that each time you flip the coin or roll the dice, it's an independent event, and it doesn't matter what's happened in the past. The odds are completely the same. Okay, 116.8. A fair coin is tossed 4 times, and it comes up heads each time. Okay, let's just write this down so we can see it. It's come up heads, 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 heads. And now the question is about the 5th coin. What is the probability it will come up heads on the next toss? Well, what did I just say up here, right? It doesn't matter what's happened in the past. Each event, each roll of the dice or flip of the coin is an independent event. The odds of a certain thing happening in that toss are exactly the same no matter what has happened in the past. So the probability of getting heads in our 5th toss are exactly what they always are, 1 out of 2. Okay? So that is the very important moral of the story. In a true and proper game of chance, the odds don't change based on what's happened in the past. The odds of each event are completely independent of all the other events. Guess what? We're done with lesson 116. I hope that felt like a nice change in your brain. And like I said, we don't really do much more with probability. We will come back to the permutations and add a bit to that, but you've gotten most of it right now. Thank you. Goodbye.